Dear students, today we are going to discuss about dipole moment. Okay, so first one, dipole moment. Dipole moment. So already we have seen in covalent bond, it is formed between two different or same atoms. So we have studied in last class polar covalent bond and non-polar covalent bond. Okay, so let us discuss about polar covalent bond. Polar covalent bond. Already in detail we have discussed, just I am telling this one. Suppose for example HCl. So when there is difference in electronegativity, electric dipoles are produced. Suppose for example hydrogen Cl. This is more electronegative. As a result, this develop partial negative. This develop partial positive. So these are called electric dipoles. So electric dipoles in a compound or a molecule is measured in terms of dipole moment. Okay, so what is dipole moment? What is the definition for dipole moment? Dipole moment is symbol is mu. Mu is equal to, it is the product of the magnitude of the charge and the distance between charge of any one of the atoms and distance between the atoms. So how we will write which one? Mu is equal to E into D. E is equal to, in some books they refer Q. They say E into D. E is charge of any one of the atom. D is called distance between the two atoms. So this is H and Cl, charge of any one atom. So it's a product of the magnitude of the charge and distance between the atom. Okay, so charge is measured in ESU and distance is measured in centimeter. So ESU is 10 raised to minus 10 ESU. This is in the order into centimeter. There is 10 raised to minus 8 centimeter. So we are getting 10 raised to minus 18 ESU centimeter. This is actually not SI unit. In SI unit we call it dBi. So 1 dBi is equal to, dBi is equal to 10 raised to minus 18 ESU centimeter. Okay, so what is dipole moment? So dipole moment is the product of the magnitude of the charge and the distance between two atoms. So charge is measured in terms of ESU. Distance is measured in terms of cm centimeter. Now it is used dBi. 1 dBi is equal to, 1 dBi is equal to, dBi is the scientist name. So 1 dBi is equal to 3.33564 into 10 raised to minus 30 coulomb meter. This is SI unit. This is not centimeter. This is coulomb meter. Okay, now we see what is the relationship between, this is not actually in the book, but just when we do application of dipole moment, we may require this ESU centimeter unit. Sometimes conversion is necessary there. So for that, just for your information, so 1 dBi is equal to 10 raised to minus 18 centimeter. Okay, 1 dBi is equal to, 1 dBi is equal to 10 raised to minus 18 ESU centimeter. 1 dBi is equal to 3.33 we can take into 10 raised to minus 30 coulomb meter. Let us see what the charge of electron, charge of one electron. One electron charge is equal to 4.8 into 10 raised to minus 10 ESU. It is in ESU. Okay, unit. Then charge of one electron in coulombs. What is this one? 1.602 into 10 raised to minus 19 coulomb. So this is COLUMB, coulomb. Okay, now we can calculate what is the value of 1 ESU. 1 ESU is equal to 1.602 into 10 raised to minus 19 divided by this unit, 4.8 into 10 raised to minus 10 is equal to, approximately we can take 1 by 3 into 10 raised to minus 9. This will go minus 9 coulomb. Okay, now see here 1 ESU. So 10 raised to minus 18 ESU. 10 raised to minus 18 ESU centimeter. Okay, we are writing this one, centimeter is equal to. How will you find out this one? 1 by 3 into 10 raised to minus 9 into 10 raised to minus 18. Here this centimeter. We are converting into meter. So you can add 10 raised to minus 2. So what you will get? 1 by 3, that is equal to 0.33 something into 10 raised to here 20 minus 29 coulomb meter. This is equal to 1 dBi. We know already 1 dBi is equal to 10 raised to minus 18 ESU centimeter. Now this is equal to 3.33564. It is sufficient, this one, into 10 raised to minus 30 coulomb meter. Okay, this conversion of unit is important because sometimes they ask the question, what is the percentage of application of dipole moment? Some problems comes. So what is the percentage of ionic character? What is the observed dipole moment? What is the observed ionic dipole moment, mu ionic? So we should know how to convert the ESU into dBi or dBi into ESU. For that it is necessary. Okay, so next one we will see. So when we see the dipole moment, how we find out the dipole moment? How we will represent the dipole moment? For example, if you are taking HCl, see here H and Cl, which is more electronegative, chlorine is more electronegative. So we are adding crossed arrow. Cross arrow means like this, arrow mark, here one cross. So where this one arrow mark is there, that shows which is more electronegative element, that arrow shows that one. This side is less electronegative element. So this will become delta plus, minus, this is delta plus. Now we will see how to calculate the dipole moment in case of diatomic molecules. So diatomic molecules, suppose for example in diatomic molecules you see here HCl I have written. So Cl is more electronegative. So dipole moment is like this one. So HCl, so this is only one bond is there. So the dipole moment of this bond is, it gives the net dipole moment of the molecule. Okay, so dipole moment of this bond. So this bond dipole. So bond dipole. Or we don't, because only one bond is there. So we can tell dipole moment of this HCl. Dipole moment of this HCl gives the net dipole moment, of the molecule, molecules. Okay, the next one. So single atom, suppose for example, very important point, if you see HCl and if you see HF, which is more electronegative, fluorine is more electronegative than chlorine. That means you see the molecule, when electronegative difference is more, If you see HF, fluorine is more electronegative than chlorine. So if the electronegative difference between two atoms is more, then that bond or that molecule will have higher or greater dipole moment. So you see example, in HCl dipole moment is 1.03. But in HF that dipole moment is 1.91 D. So first one, what we can understand, in dipole moment of diatomic molecule, the dipole moment of that bond, it gives the net dipole moment of the molecule. Okay, when electronegativity difference between the two atoms increases, then they will have larger dipole moments. Okay, I think you understood in case of diatomic molecule. Now we will see polyatomic molecule. What is polyatomic molecule? More than two atoms. So you may get the question like this one. Some molecules have 3 atoms, but one of the molecule may have 0 dipole moment or other may have dipole moment. So in this case, in polyatomic molecule, we take carbon dioxide. So carbon dioxide, you see C double bond O, C double bond O. Okay, so different, this you see, when you see this dipole moment, what is given here, mu is equal to 0. But in polyatomic molecule, there may be 2 or 3 polar bonds will be there. What is polar bonds? When electronegative difference between two atoms is different, then we call which one? Polar. Each bond may be polar, but as a result, the dipole moment of the molecule may be 0. So you see here, C double bond O. C double bond O. So this C double bond O, this is polar. This C double bond O, this is also polar. But what is happening which one? For this one, so when we calculate the dipole moment in polyatomic molecule, we calculate the dipoles of the each individual bonds. So individual bonds dipoles, it is called bond dipoles. Is it clear? We don't call it dipole moment, we call it dipole moment of the each bond is known as bond dipoles. Bond dipoles. So here what is this one? Oxygen is more electronegative. So we'll put the bond like this one here. So here we'll put here like this one. So what happened this one? The bond dipole of C double bond O is 2.3D, something like that. Okay, the bond dipole of carbon dioxide in bond dipoles of C double bond O is 2.3D. So this C double bond O is 2.3D. Then you see this C double bond O also 2.3D. But both are both are equal also, because why it is equal? This bond, both the atoms are same, so both the bond dipoles are equal and opposite, because the molecule is linear in shape. So the bond dipole of one atom, one bond dipoles, the same value and the other bond dipoles, but what happened this one? Both are in opposite direction. So the both the bond dipoles gets cancelled. As a result, you have the dipole moment of carbon dioxide is 0. Is it clear? So in carbon dioxide, how many atoms are there? 1, 2, 3. So 3 atoms, but the bond dipoles are 0. As a result, the net dipole moment or resultant dipole moment, you can see CO is polar in nature. So each bond is polar. So each bond, individual bond, for that we call it bond dipoles. So 2 individual bonds are there, C double bond O, C double bond O. So the bond dipoles of each CO bond is 2.3D. So this is for explanation, I am giving the value. Value is not necessary, but in the question they may give the value. It is not necessary to by heart this value. Okay, so you should understand. So this act in this direction, this also this direction. So both the bond dipoles are equal and they are in opposite direction. As a result, the net dipole moment of the molecule is 0. Is it clear? Now let us go another example for water molecule. Water molecule, you see, what is happening here in water, this bond angle of water is 104.5 degree. We will study in later. 104.5 degree. So this is bond dipole. So 2OH bond dipoles are there, bond dipoles, and they have lone pairs also. So these two OH bond dipoles are at the distance or at an angle of 104.5 degree. But they do not get cancelled because they are not in opposite direction. As a result, they will have resultant dipole moment. The resultant dipole moment is not 0, it is 1.83 D. So here you see water also, if you take water H2O, it also contains 3 atoms. This carbon dioxide, this also contains 3 atoms. Okay, but they have 3 atoms, but in case of carbon dioxide, the resultant dipole moment or net dipole moment is 0. In case of water, it is not 0. Is it clear? Now next let us see what is the net dipole moment of BF3. BF3 you see here, BF3, B, F here, F here, F. So this is more electronegative, more electronegative, more electronegative. Here you see they have symmetrical structure. So if you see this one, here the bond this resultant dipole moment is 0. Here you see what is happening here, which one? This is one bond dipole, this is another bond dipole, this is another bond dipole. So how many bond dipoles are there? 3 bond dipoles are there. The sum of, you see, the dipole moment is the vector quantity. What is vector quantity? It has magnitude as well as direction. So when we calculate the dipole moment, we have to find out the dipoles of each polar bonds also, and also we have to find out, we should know the geometry of the molecule also. So geometry of the molecule also plays an important role there. So if you see this one, the any two bond dipoles of BF, bond dipoles of BF is equal and the sum equal and opposite to the third one. Opposite to the third one. That means you see the bond dipoles here, the bond dipoles, the sum of any two bond dipoles of BF is equal and opposite to the third one according to parallelogram forces. Okay, as a result, what happened this one, when you join this one, you take the sum of these two bonds, you will get some value that is equal and opposite to the third one. As a result, the dipole moment of mu BF3 is 0. Is it clear? Next we will go for the dipole moment, how we calculate the dipole moment of NF3 and NH3. Now let us see what is the dipole moment of, how dipole acts in dipole moment of NF3 and NH3. Okay, let us draw the structure of NF3 and NH3. Suppose the first one you see here, NH3 will see ammonia. So ammonia structure, when you draw this one, N, here H, here H, here H. Here you see lone pair is there. So what is happening? More electronegative, this also more electronegative, this also more electronegative. So here this, when you calculate the dipole moment in ammonia, 3 bonds are there. That means 3 dipoles. The dipoles of 3 NH bonds. Okay, the dipoles of 3 NH bond and the orbital dipole of lone pair. The orbital dipole of lone pair So you see the orbital dipole of lone pair act in same direction as dipole of 3 NH bonds, they act also in same direction. You see this also in same direction, this also in same direction. So as a result, so when we calculate the dipole moment of the molecule which contain lone pair, we should calculate the value of dipole moment, orbital dipoles of lone pair also. So here what is happening here, which one? Dipole moment of ammonia as a net dipole moment is 1.46 dpi. Right? See here, this is acting in this direction. These three are acting in same direction. Then orbital moment of dipole of lone pair also acting in same direction. So as a result, NH3 has 1.46 dpi. But now you see here in NF3, what is happening? Which one? Orbital, you see NF3, N, F, F, F. Here lone pair. Okay, this is more electronegative, so it comes like this direction, this one. So this also here. Okay, this act in this direction. So here what is this? If you observe the molecule, you can see the dipole moment, the bond dipoles of NF bond. You know, fluorine is more electronegative than nitrogen. So the cross arrow comes this one. So the bond dipoles of NF bonds are in this direction. The bond dipoles of lone pair only one pair here. Okay, one pair. Lone pair, that is in the opposite direction. As a result, the net dipole moment or resultant dipole moment is lesser. So what is the value? Net dipole moment is 0.25D. 25D. Is it clear? So both have. So the question may come like this one. NF3, it has 4 atoms. This also 4 atoms. If you study the geometry, both are pyramidal in structure. But the net dipole moment of NF3 is much lesser than ammonia. What is the reason? The bond dipoles of 3 NF bonds are in opposite to the orbital dipole moment of orbital dipoles of lone pair. As a result, they have lesser net dipole moment than NH3. Okay, the next we will see now the remaining thing, the applications of dipole moment, that we will see in next video. Okay, thank you.